Alright, hell yeah. So what we have here is, I want to simplify a rotational problem. And heck yeah. So this is very similar to, like, hey, just dropping this mass off a cliff. It has a force of gravity, so we have mg on it. You know what I mean? If this is a mass of 1 kilogram, gravity is 10. 10 meters per second, And so heck yeah. So this force is going to be 10 newtons. Cool. So we got a 10 newtons force right there. Same thing over here. You know what I mean? So we have mg, 10 newton force. So we use our free body diagram. Or I mean, I guess if we did a free body diagram of this one, hey, we might have some tension. Obviously, in this location, we probably don't. And then we have this 10 newtons down. So we want to sum forces in the y direction. And I'm just going to say this is the positive y. And we have mass times acceleration. And then so for this, you know, this is the only force in the y. Tension's not in the y. And so we have 10 newtons is equal to that 1 kilogram mass. And then we just have the acceleration. I'm just going to call it a. And then we can rearrange. And yeah, let's do this, you know, kind of 100%. So we have 10 newtons divided by 1 kilogram, because you're like, well, what the hell's that? You know what I mean? So then you have to kind of go back to your F equals ma equation, do this maybe, and say like, hey, what are the units on it? So I'm going to say we have 1 newton is equal to, sometimes this is the little dot you can designate, hey, I'm just doing units. And then so we have 1 kilogram. 1 meter per second squared. Now you can rearrange this 3 ways. You know, anytime you get an equation with 3 different things, let's rearrange it. So let's solve for 1 kilogram. So we have 1 kilogram is equal to 1 newton divided by 1 meter per second squared. Cool. Now let's solve for 1 meter per second squared. 1 meter per second squared is equal to 1 newton divided by 1 kilogram. Oh, okay, hell yeah. So that checks our box, because we have 1 newton divided by 1 kilogram. I mean, we got 10 newtons divided by 1 kilogram. But even just this, hey, this is 10 times 1 newton divided by 1 kilogram. You know what I mean? So heck yeah, you have this 1 newton 1 kilogram thing. You just have a multiple of 10 of it. So we can change this units. So this is now 10 times 1 meter per second squared. You know what I mean? Sometimes doing like the simple stuff kind of 100%, you know, kind of really helps your intuition. But anyway, that was a little side tangent. So yeah, okay, so we have the acceleration of 10 meters per second. And that's what we would expect in, for sure, this example. And heck yeah, this is in free fall. You know what I mean? The tension's going this way, but for a split second, it's going straight down. Okay, but this problem, you know what I mean, it gets a little bit trickier, because as you're swinging this loop, let's say you're just down here, you know what I mean, and now the rope's totally right there. Let's do the free body diagram on this. You still have gravity. Gravity always points towards the center. The center of this mass always points towards the center of the Earth. So now this free body diagram is totally different. You know, I mean, we have that 10 newtons down, but then we have a tension force going upwards. And what do we see at the bottom of this arc? We are no longer traveling in this A direction. So sometimes F equals ma, I like to throw eyeballs on this side, because sometimes just by demonstration, you know what's going on with the problem. You know that right here, acceleration is 0, and that means this side of the equation has to sum to 0. Sure, we can have a force. You can have mg, you know, but if you just had this force, it'd be traveling across the universe and speeding up. So we need this tension force to balance. So heck yeah. But what I want to do is run. What I really like to do is say, hey, so like back to here. Hey, I have this force of mg, and it's going to be, let's say, in the positive direction. Cool. And that's going to equal mass times acceleration. All right, hell yeah. And then, you know, so for this one, yeah, we solve for acceleration, and we get g, and that's going to be that 10 meters per second. Okay. And obviously we, you know, up here we already solved for mg. But anyway, And then what this means, the acceleration says, hey, it's going to change velocity of 10 meters per second in 1 second. Well, let's say you do run F equals ma and you get a number for a. And that's going to be in meters per second. That's going to be the change in velocity every second. And what I like to do visually is just run the problem for 1 second. You know what I mean? So if we ran this problem for 1 second, this thing is going 10 meters per second. So cool. So let's go over here to this one. So this one is velocity 0. We know the acceleration is 10 meters per second every second. So heck yeah, now we're down here. Now we're going 10 meters per second. So this was time 0. This was time 1 second. Okay, so now we know, the question is well, how far did we go? You know what I mean? You should always ask that. And well, we were going 0 miles an hour, or meters per second up here. But we're going 10 here. We weren't going 10 the entire way. You know what I mean? So this is such a good one just to always do mentally, is that, hey, our average velocity is 5 meters per second. And if that doesn't just pop into your head, actually a few different ways, you know what I mean? But heck yeah, so this is our average velocity for that 1 second, and it looks like we traveled a distance of 5 meters. So cool, so that's 5 meters. But this is where this gets mentally doesn't make sense for this. Running this problem for 1 second, holy hell, this is 1 meter. You know what I mean? So, you know what I mean? If the diameter is 2 times pi is going to be 6.28. So there's a circumference of this circle of 6.28. And we're going 5 meters. You know what I mean? So this thing already whooped all the way around here. And we know that acceleration isn't going to be the same down here as it is right there. So that's the only thing about this problem where it's just it's kind of hard to visualize. And then all right, so here's kind of my method to whoops, this is 1 meter. Here's going to be my method to kind of simplify this. And we get we get to learn kind of a little bit about impulse, because what I was doing is saying this is 10 newtons, and I'm going to say, hey, we got the force is equal to mass times acceleration. But then I got a number for acceleration. Remember that it was 10 meters per second, and I just said, well, I'm just going to run the problem for 1 second. If that's going to be my acceleration, after 1 second, I know my velocity is just that number. You know what I mean? Because this is the number divided by 1 second. So run it for 1 second. Hell yeah, whatever this number for acceleration is. You know what I mean? So I can say acceleration is basically, the magnitude of acceleration is equal to the magnitude of velocity. I don't think you can actually say that. Magnitudes doesn't change the units or whatever, but you get it. Yeah, the number on acceleration is equal to the number on velocity. Cool. Okay, so how did we do that? Because if we have force is equal to, so we changed this into force is equal to mass times change in velocity, change in time. Cool, and so we got that. So how did we get 10 meters per second out of this? Well, we took the acceleration of 10 meters per second, and then just multiplied by 1 second. So seconds canceled, and then we got 10 meters per second. So if we did that to this side of the equation, multiplied by 1 second, we do that to this side, 1 second. So this is saying, hey, we have a force that's going for 1 second, and that's going to be equal to mass, and then we have a change in velocity, change in time, times 1 second. And what we see that what this gives us, these kind of cancel, because this is just like a placeholder for 1 second, just like units-wise. And so we get mass, and then we can just say the change in velocity is that velocity that we want after 1 second. So we just have mass is equal to that velocity, and this is force still times 1 second. So we get the equation for impulse is just like, hey, force times time is equal to mass. And now this would be change in velocity, but if we're only running it for 1 second, I guess if our initial velocity is 0, we can run this for as many seconds as we want. But if our initial velocity for, a lot of problems start at rest, you know what I mean? And then so I can just say, hey, force times time is equal to mass times velocity. But here's the deal, is I don't particularly like this equation. I mean, just from the fact that I don't think it's super intuitive. You know what I mean? I like the aspect that if we have a force on a mass, it's going to change its velocity. You know what I mean? Just from that perspective is kind of where I think, cause in physics, that's why you go the simplistic routes of energy and just all different other sorts of equations that make it simpler. But I guess I don't know. It seems like what is my strategy in life? Is my strategy not to make it simple? I think that my strategy is to make it more intuitive. So even if that requires a lot of more work to make it intuitive, I want to do that work to make it intuitive. But then we do stuff like this of just like, I guess, I mean, if I'm just running this for 1 second, it's synonymous with it. I can just say force is equal to mass times velocity. You know what I mean? So this is kind of what I'm doing. But we are gonna kind of modify it because if I run this for 1 second, this thing's gonna whoop all the way around here and it's gonna be up there. And visually, I don't want that. But I know it works. I know at least if I at least run it, like that's going to be the acceleration. But then here's the issue: is that like for this problem, hey, maybe I want to know the angular speed. So we have angular speed in radians per second. And I swear, the only way I can know this equation is like, hey, radians per second times radius gives me something normal, because no one knows what radians are. So anyway, so this gives me the tangential velocity. And so if I have omega r times the tangential velocity, that'll give me the angular speed. So like initially, my velocity is 0. That means my angular speed is 0. Run it for 1 second. Whoa, I'm up here. I have a tangential velocity of 10 meters per second. Cool. So that's going to be this. So I can just rearrange this equation for omega, and I can get velocity tangential divided by r. Omega is 10 meters per second divided by 1 meter. And radians per second is dimensionless in the distance. And it's just a function of, time. So it's 10 radians per second. So heck yeah, but my only just mental hang-up is just like, well, visually that's not what's happening. If this thing's up there, it didn't have that same, like after this thing gets to here or here is drastically different. The acceleration isn't the same. So that's where I guess I probably just should have started the video from here. But what we want to do is just like, hey, like how, well, kind of a couple things. So we have 1 kilogram and then 1 meter. So if I just run this thing for like just a split second, and now this thing gets to there, it pretty much just traveled linearly. You know what I mean? It pretty much just traveled up and down. It really didn't travel that way a hell of a lot. And this is kind of provable with just how degrees work and circles and the geometry of it. Like it's basically just moving vertical. But we said that in 1 second is going to get up there. So how like what do we need to modify our seconds to make it drop to that? I'm just going to do like 1/1000th of an inch. You know what I mean? So we're going to go F equals ma. I still have mg on this. And then so we still have mg on this side. Well, let's hold on. I'm just going to run this force for 1/1000th of a second. And hell yeah, so that's going to give me, and if this is mass times a change in velocity, change in time. So I'm going to have mass, change in velocity, change in time, and I'm going to multiply this by 1/1000th of a second. You know what I mean? Or more formally, if this is acceleration, I'm going to have a number that says meters per second per 1 second. And so I'm just going to multiply by a thousandth of a second. Seconds are going to cancel. And hell yeah, I'm going to get that number for my change in velocity. Initially, velocity is 0, so whatever that number is, mv is what the velocity is going to be at. So this whole thing right here, if I knew the acceleration and I multiplied it by a thousandth of a second, this is going to be my velocity at time thousandths of a second. So this is not mv times 0.01. That would have to be the velocity. How am I getting messed up? Because this is acceleration. We know that's going to be like 10. And so, but yeah. So, I don't know why I mentally get confused on this stuff. But anyway, I guess because I'm just trying to do something different. Okay, so we're going to run this force for a thousandth of a second, and we're going to get that velocity. Okay, so now let's do the cliff analogy. And now what are we talking about by running this force for a thousandth of a second? So we have mg. What I'm going to do is well, actually no, this one's straightforward. So I better slow down. So I better do it like I did the equation. So we have mg, and we're going to multiply by 0.0 thousandths of a second, and then we're going to have that mass times that velocity, at that time. And then that's what we kind of want to find. And so here we have 1 kilogram, 10 meters per second squared, 0.001 seconds, and then this mass, 1 kilogram. And then just that velocity. So the 1 kilogram cancels, and this meters per second squared, one of those seconds is going to cancel, and we're going to get units of meters per second. This 10 is going to go to 1, 2, 3 of 0.01 meters per second. So that's going to be our velocity. That's going to be our velocity at that time. So now we can say, hey, our velocity at that time is 0.01 seconds. And our velocity initially is 0. So we went from 0 to this velocity, so our average velocity is 0.0. And sometimes you don't know how to do like that divided by 2. So we go, just throw a 0 on it and be like, oh, there's a 10 here. And then so that 10 is going to go to 5. So heck yeah. So the average velocity is 0.005. So 5 thousandths of a meter per second. Cool. And we didn't travel for a full second. We only traveled for a thousandth of a second. So our distance is going to be that average velocity times that thousandths of a second. So we're going to have 0.005 meters per second times, and this is where even just writing an equation, average velocity times time, is like, I don't think that's useful or helpful. I think it's helpful to be like, okay, just say, hey, I have an average velocity, and I did this for that much time. That's the intuitive approach, So, and I probably made this hella too small, because now we have a thousandth of a second, and we're only going very slow. So we got 0.005 times 0.001. And so I'm going to give up on this problem, and we're just going to run it for... because that's too small for my brain to handle right now. It's multiply by 1,000, so we went 0.005 millimeters. That's not what I wanted to do. I wanted to go about a millimeter. So I struck out there. So heck yeah. So now just I know that I can run this for maybe a hundredth of a second. Actually, let's just do it for a tenth of a second. That would be cool if it worked out. So we're going to do force times 0.1 seconds is mass times that velocity at that time, and we're going to have 10 newtons, or I guess you could say this is mg, 0.1 seconds is equal to m that time. And so the masses cancel. And so we have 10, and this is going to be 10 meters per second. So we have 1 meters per second squared. Holy hell. So this is going to be 10 meters per second squared times 0.1 second. One of these seconds is going to cancel. We're going to get a velocity of 1 meter per second after we multiply by this 0.1. And so, heck yeah, so we get a velocity of 1 meter per second. Our average velocity, so now this is, and I put the wrong terms on there. So now we have a velocity of 1 meter per second. Our average velocity is 0.5 meters per second, and we did this for 1/10 of a second. You know what I mean? So we didn't go 0.5 meters per second for a full second. That would have been 0.5 meters. We did it for 1/10 of a second, so we went 0.05 meters. Cool. And then so 0.05 times 1,000. So we went 50. We went 50 millimeters. You know what I mean? And that's about 2 inches. So this is 40 inches, and we went 2 inches. You know what I mean? So inverse tangent of 2 divided by 40. We did like about 2.86 degrees. And if we did 2.86 degrees, then and if this was our how does that work? How does that work? Yeah, I'm just gonna call it good. Oh no, let's do this. Holy Toledo. You know what I mean? Anytime you do some trigonometry where you just like, nah, I give up. So these two are the same. 1 meter, 1 meter. And then so we swept it out this way. And then so we're going to draw a vertical line here. And now we know this 1 meter is all the way out to here. But when we sweep it out, we are traveling that way a little bit. And then so we have this angle. It's 2 degrees. I'm going to store it as theta. And so now I want to know this distance. You know what I mean? And so that'd be the easiest thing. It's going to be 1 cosine of that angle. So it's just cosine of that angle. And then, so this distance is 0.99875. Okay, so hey, what's this distance? Because this distance right here is the distance that we traveled that way. It is super negligible. So that's going to be this total distance 1 minus that. So 1 minus that. Cool. So we went, and then multiply by 1,000. So we went 50 millimeters down, and then we only went 1.24 millimeters that way. That's imperceptible. So if you have you know what I mean, this setup, kind of like a golf ball at 1 meter on a string, and then at 1 meter, about 40 inches, and then you drop it for 2 inches. In that 2 inches, it will only move 1.24 millimeters that way. So hell yeah. So now we have kind of a scenario where, you know what I mean, it jives. You know, we're going to say, hey, this is our this is our tangential velocity. Now let's find our omega. Our omega is going to be the same. It's just we're just doing this just for our mental sake. And I probably haven't been doing a good job, but so here we go. So we have this scenario. We got that 2.86 degrees, and this is going to be after time of 1/10 of a second, like 0.1 seconds, and we're going to go from velocity 0 to a velocity of 1 meter per second. Cool. So now our omega, our angular velocity here in radians per second, we're not going any. 0 radians per second. Now what's our omega after 0.1 seconds? So angular velocity in radians per second. Radians times radius is something normal as tangential velocity. I want to solve for angular velocity. So I'm going to say angular velocity is this tangential velocity divided by the radius. I found the tangential velocity after this 1/10 of a second. It was 1 meter per second. So my angular speed right here is going to be it's going to be different, but yeah, that's cool. We want it to be, because okay. So, and that's going to be a velocity of 1 meter per second divided by 1 meter. So we're going a speed of 1 radian per second right here. But that's not what we want. What we actually want is the acceleration. You know what I mean? The angular acceleration. And so what's our angular acceleration? Definitionally, it's the same thing as acceleration. Acceleration is change in velocity, change in time. So angular acceleration is change in angular velocity, change in time. So we changed our angular velocity. We went from 0 to 1 radian per second. So cool. So we have that. But guess what? We did that in 1/10 of a second. So divided by 0.1 seconds. And now you see that our angular acceleration is 10 radians per second squared. And I guess I didn't do that for that initial problem, you know what I mean? So now mentally, you know what I mean, hey, after 1 second, yeah, this thing's going to be way the hell up there. But you know, still you can do that mentally. You can say we have a driving force of mg, F is equal to ma, we have mg is equal to ma. Our acceleration, is g, which is 10 meters per second squared. And then our velocity right here is 0. What this means is that if you're neglecting the string, you know what I mean? Hey, we're just going to fall, and we're going to fall 10 meters per second. But now we're just going to say, well, we're going to include the string, but now we're going to whoop around that 10 meters. And to go 10 meters, no, you're not going to go 10 meters. Your velocity is going to change. So after 1 second, you're going to go from 0 meters per second to 10 meters per second. Average velocity is 5 meters per second, and you did this for 1 second. Time is 0, time is 1. And so you went a distance of 5 meters. So we're saying in this, hey, you whooped around 5 meters, but you're way up there, and that it seems nonsensical, but you can still do it that way. And so up here, we had a tangential velocity of 10 meters per second, and we had a tangential velocity here of 0. Our radians is 0 radians per second here. And then I still have to do the equation every time. Radians times radius is tangential velocity. And I want to know my omega up here. So omega is velocity tangential divided by the radius. That's going to be 10 meters per second divided by 1 meter. And we have 10 radians per second. Cool. But let's say we want to know our angular acceleration. Our angular acceleration is going to be the change in angular speed. We went from 0 to 10, so we went 10 radians per second, and we did that in a time of 1 second. And so we still get an angular acceleration of 10 radians. Sorry, the seconds don't cancel, they're additive. So we have 10, or multiplicative, or whatever. We have angular acceleration of 10 radians per second squared. So cool. So I was just making this video because sometimes I like to do rotational problems and make them simpler like this, and just say, hey, yeah, obviously it's gonna be falling in free fall, and so after 1 second I can figure out its velocity. But that thing's going to be way the hell up here, and so for my brain it just kind of seemed nonsensical. So the only thing that I'm not going to do it. I'm probably not going to do it this way where we run it for 1/10 of a second or 100th of a second. But I did it that way just so like my brain won't melt just by doing it this way. And all we're doing is we're getting the instantaneous angular acceleration. We're getting the instantaneous acceleration. But I just think, hey, if you have an acceleration that's, let's say, 10 meters per second, you know what I mean? Hey, it seems like it shouldn't change that much in 1 second. And for a lot of things, like even driving in your car or something, hey, your acceleration doesn't change that much. But holy Toledo, this wigged me out, because it's just like, yeah, this changes a lot. The acceleration goes from, you know what I mean, this direction 10 meters to none, to 0. It's 0, and then the opposite. You know what I mean? And now it's going yeah. So, or I mean, I guess it's always the acceleration is always downward, but then it's 0 value here, and then it's still downward here, because you're changing your velocity, you're slowing down. So anyway, but yeah. So I don't know if this video made any sense, and we'll see if I, kind of modify this or reference this later. Alright, so thanks for joining me, and that's a video.